Hi everyone. So today we're going to talk about basically how to, I'm going to show just a quick demo to supplement the frequency lab, how to analyze that data, how you're going to kind of accomplish this assignment. It's a kind of a nice, basically a philosophical question. How do you do a lab without actually doing the lab? So again, don't worry too much about it. We're going to kind of take it step by step. And what we're going to do today is basically go through how you want to kind of approach this lab, how you want to kind of analyze this data, and we'll take it step at a time. So the first thing first, you want to kind of go to Canvas and make sure to kind of pull out, basically look at the assignments, and you want to go to the frequency lab. So if we go into this frequency lab setting here, you could see basically you still have your lab report evaluation. You could kind of preview and look at basically how the lab is described. And you can take a peek there in terms of what is kind of expected in terms of what we're going to be talking about here. So we'll take a look at that a little bit later. Sorry about that. So basics, again, your lab handout, read that ahead of time. You can kind of get some insight into how the labs performed. We're going to actually take a peek at some really nice schematic of how the lab performed in just a second. But so that's your lab handout, lab report evaluation, and then more importantly, you can see the zip file with the data, and then also basically this Mathematica notebook here that, again, guides you through it. And actually, I'll pull it right here. You can see very well documented, unlike my usual Mathematica notebooks. So this walks you through basically what I'm going to try to talk about today in more detail. But again, I just want you to see kind of how I import the data, analyze, and we'll kind of talk a little bit more about some of this analysis in a second. So with that, let's start with first thing first. We need to download the zip file. So I'm going to download it. I need to make sure I extract all the data here. So you look at the data files. You see the notation, this name. LP means L is length, and then 0.36 meters. So that's kind of the notation here. All in this lab, we are changing the length of this beam, and we are going to kind of analyze how this changes the fundamental frequency or the resonant frequency. So again, make sure to read that lab handout, and we'll kind of move forward here. So right now, I just want to extract this data, and I'm going to extract it to my desktop here. So instead of the downloads, I just want it on my desktop. Make our life a little bit easier. So with that, let's see if I can look at the desktop. Of course, I have so many notebooks available, and actually it's on another screen, but believe me, it's on the desktop. I'm using multiple monitors here. So let's kind of go back and let's start to, before we get started on actually writing in Mathematica notebook, let's take a look at what we're going to be performing in this lab. So we are going to basically, or what we would have done in class, we are going to attach this aluminum beam here to the edge of a desk. We're going to put an accelerometer on this beam. We're going to apply a force and deflect the beam at a certain length, and you're going to kind of clamp this here. The accelerometer is, once you deflect the beam and you release it, it is going to undergo some acceleration as the beam deflects and basically vibrates. And depending on the length of that beam, the resonant frequency, which is the dominant frequency in your Fourier spectrum, you're going to calculate the acceleration data. Then you'll perform, and actually what we're going to perform is a discrete Fourier transform of that data. We're going to figure out the frequency spectrum and then look at the resonant frequency and see how that changes basically as a function of your length. So we are going to measure, and the data that we have is for the experimental frequency. So we're going to calculate the experimental frequency from this discrete Fourier transform, but we also have, looking at the lab report, we have a function that gives us the theoretical frequency for a cantilever beam. So a cantilever beam, the assumptions that we're making here is a cantilever beam is unitless, a cantilever beam is rigid, i.e. not elastic, and basically it's massless. So there are some problems with that, right? Obviously this is not a massless beam. Additionally, one of the kind of differences between our lab experiment and kind of real life, or the theory and the experimental values, an aluminum beam, we're going to get to this in the mechanics lecture in just a bit, it is not rigid, it is elastic. So it will undergo some basically elastic deformation and even plastic deformation as well. So you want to make sure when you do your experiment to not plastically deform it. That will mess up basically the vibrational properties of your beam, but we did not do that when we ran this experiment. So that's kind of some of the key differences. Additionally, this equation does not account for the fact that we're putting an additional mass on our beam as well. So when you put that accelerometer on your beam, obviously that's some additional mass. It might affect your basically frequency measurements. So if the theory and the experimental data do not overlap, if those error bars, the total uncertainty error bars overlap or do not overlap, those are some of the rationales as to why that might be the case. So we could talk a little bit more about that during our lab sessions, but that's the basics of this lab. So please make sure to kind of read this and we'll kind of go and kind of calculate all these values now and look in the Mathematica notebook. So I am going to go ahead and get this started right now. So I'm going to start with a basically clean Mathematica notebook, and we are going to start to kind of basically bring in my data. So first things first, I want to have that that equation that I was working with previously. So I want to bring in my equation for the frequency of my beam is going to be, this is just from the lab handout, 1 over 2 pi times L squared, excuse me, squared, and then times square root of 12 times y is going to be my Young's modulus. Actually, 12 times y times inertia divided by rho is my density of my aluminum times the area, which is my width, times height. So that is my kind of fundamental equation here for the frequency. So let's take a peek at how that looks. I'm going to do full simplify. Excuse me. And that's how it works like now. But again, we could clean that up just a little bit. So I know that inertia for a cantilever beam, the moment of inertia, is going to be the width in this notation times the height, which in this lab is basically the thickness. So again, you all hopefully taking mechanics and materials, you're all mechanical engineers, bioengineers, you're experts on this stuff. Again, I'm just a material scientist. So, I'll leave the beam bending, mode of inertia, all that stuff up to you. But now we can look at our equation here, and now we're left with kind of our simplified version of frequency. So how many independent variables do we have? We need to calculate the bias error, right? So the bias error in this equation, because again, we are going to measure essentially these lengths. So what are the independent variables that we have available to us? So frequency is a function of h, y, rho, and L. All of these values have some uncertainty. So the uncertainties are listed in that kind of Mathematica notebook that I posted online. So to calculate the bias error here, we know that we're going to have to do what? Hopefully I can hear all the groans already over my remote teaching desktop. Yeah, that's right. You're going to have to calculate all those partials, right? The partial of every variable that has some uncertainty associated with it. So Young's modulus for aluminum is pretty well characterized. It's usually 69 gigapascals. But again, anytime you make a measurement, there's going to be some uncertainty in that value. Again, I give you the uncertainty as well. Density, again, there's still some uncertainty in density. Even those are kind of like tabulated standard nominal values. But we know there's definitely going to be some error in the measurements of our height and our length as well. So that's what we're going to kind of deal with in this lab. But to calculate the bias errors, we need to take the partial derivative. So I'll start first with length. So I'm going to assign a variable. So remember in Mathematica, if things are blue, they are undefined variables. So I'm going to create this variable. So the partial of f with respect to L, so that's what dfl means. So I'm going to take the derivative, capital D, with respect to f. The function, I'm going to take the derivative of the function f with respect to L. I'm going to close this, and I'm going to shift enter. Remember, you have to shift enter each time in order to get your output. So there's my partial with respect to L. I can do the same thing, dfh. D times f and h. This is just to double check. You can do this by hand, obviously, but again, why do math by hand when you have Mathematica at your disposal? You could full simplify to make it look a little bit nicer. Again, it doesn't full simplify quite enough to my liking. Sometimes you can play around with simplify, but again, it doesn't matter too much. So to calculate your bias error, you need to do all those partial derivatives. You need to put it into your total uncertainty equation and figure that out yourself. So in terms of the precision error, I only measure these values once, so there's no precision error for the, again, this is the theoretical frequency. So that takes care of all of that. So now I need to move on and figure out, okay, well, what is my, how am I going to deal with the experimental frequency? So in order to do that, I need to first to kind of take a look at what is my experimental frequency data looking like. So experimental frequency. And really, this isn't the experimental frequency. I want to calculate the experimental frequency, but I'm going to look at basically my accelerometer data. Accelerometer. You know I can't spell. Oh, look, I was lucky this time. So I'm just going to copy the file path from my desktop. So I just copied that elsewhere. So again, you just kind of copy and paste. For Mac users, I think there's a way to kind of, you can't just kind of unfortunately copy and paste. You have to insert the file path, but you could kind of copy that multiple times. But again, if you run into issues, just email me and we can figure that out together. So let me take a look at this first data. So this is the data of one run. So this is, the length is 0.36 meters. And I'm going to look at basically one value, the first run. So these are repeated multiple times. So obviously for the experimental frequency, you're going to have precision here because you have multiple runs of the data. And we'll talk about bias there in just a second. But let's look at the data first. So looking at this data, I don't like that format because there's multiple, basically multiple parentheses. So I'm going to flatten, which is basically removing one of those parentheses or some of those parentheses. Excuse me for the noise. I'm getting furious emails. So please bear with me. So now this is looking a little bit better, and we can kind of look at it a little bit nicer form, table form. Excellent. So on the first column, we have our time, and this is our time in seconds. Here we have our acceleration. This is our acceleration in meters per second squared. So this is the acceleration of the beam in the second column now. So that's pretty nice. I want to just take a look at, I'm interested in this data. I want to see how the beam oscillated, and I just want to kind of look and analyze this data and just visualize it. So I'm going to look and take that data in this format. I'm going to copy here. I'm just going to call this my data. So now I want to do a list line plot. List line plot. And that's what it looks like. So you see kind of this acceleration data. I'm going to look at it a little bit. Again, I want to make my, we use mathematics because we can make plots nice and pretty. So plot range all. I want to, so many emails. Sorry. True. I want to get frame. I want my image size to be large so that you all can hopefully see this. And I apologize if the text is too small, but we can zoom into the video. I want frame style. I want directive. I want it to be thickness. Again, these are just, you can always play around with these settings. Again, Mathematica is, it's easy to plot once you've played around with it enough. But it takes some time. But don't be too concerned. Just, pick a standard and a plot and just go with it. You can make it nicer for depending on whatever application or whatever you're trying to, whatever paper you're trying to write. You could adapt it for what you need, but for our labs, just stick with the template that we've been using so far, and add your own flair to it. Again, depending on the time that you have, it makes, again, the more you practice this, the better you get, and the nicer some of these plots look. So this looks pretty nice. I like this plot. Again, I have to label this, I have to label this in our, kind of notation, but we can deal with that a little bit later. So, and actually, I should have just used that. Yep. So this is our plot. So you could do list line plot, or you could just leave it as list plot. So you could kind of leave it like that. It looks a little bit harder to kind of see, but again, that's our data in a nutshell. So I like the list line plot a little bit better. List line plot. And that's our frequency data, or this is our acceleration data. So we need to, again, our whole point is we need to try to figure out what is the fundamental frequency, what is the dominant frequency, or the resonant frequency of our beam at different lengths. So I need to perform Fourier analysis. So I want to, before I even get started, I want to figure out and kind of check basically the values of my signal here. So I want to make sure that I am able to kind of calculate some of these kind of key values. So one quick thing I want to kind of put in here is I want to first look at the time data. So let's take a peek at that and look at our time data. So the time data is just going to be, so this is my data. So the time is just my first column. So again, I'm just going to grab all of the rows from the first column. And that's my time data. So I'm going to call that TDAT. So this is my time data. So from that, now I can start to get some information about how this material, or how, what was my sampling frequency? What was my period? All that kind of good stuff. So if I want to find my delta t, all I have to do is take the differences. So differences basically takes the differences between successive points in your list of time data. So I want the differences of t dat. You see it's all 0.2. You can just take the mean of this to get a single value. So our delta t is 0.02 seconds. Now, how do I calculate the sampling frequency, fs? Well, we know from our kind of other videos that we talked about, it's just going to be delta t, 1 over delta t. And now, that is our sampling frequency, 50 hertz. What is our number of points? So what is big N? You notice I can't use N here. N is already black. It is a predefined function in Mathematica, so I cannot use that. You always be careful when you're kind of assigning variables. So I'm just going to use this big N. It's not elegant, but we're going to have to deal with it. Big N, the total number of points. Well, I'm just going to take the length of t. That's going to give me how many points I have in this scenario. So 101 points. What is my period? Well, I'm just going to take the last data point. Because that is going to be my period. This is not, I can't really tell in here if it's periodic. I'm just going to analyze the signal as is. So I'm going to take -1, which is the last element in my list. That's my period, 2 seconds. What is my delta F? My fundamental frequency? Well, that's going to be 1 over my period. There we go. 0.5 hertz. So that is my delta F. That is my frequency resolution. It's my fundamental frequency. So I can only resolve frequencies in 0.5 intervals. So if you calculate, and we're going to see and calculate what is F in a second, what is our basically theoretical frequency for this beam. We're going to deal with that in a second, but we can only basically measure frequencies at 0.5 intervals. So if it's in between there, we might have to deal with spectral leakage. So you just want to mention that in your report. And that, obviously if we had, there's a limit to essentially how fast and how many number of samples we could kind of take with our data acquisition devices. So if we had, this amazing, super expensive DAC, we could shrink that delta F by just increasing your number of points N. So big N is, again, the way that you can shrink that delta F, because delta F is also Fs over N, the total number of points that you have there. So just something to be aware of. So now let's calculate our kind of DFT. So for the DFT, we really just need our kind of y coordinates, right? So I need to take basically I want the acceleration data. So just like looking back at our data, if I want the acceleration, I want all the rows of the second column. So this is my acceleration data, ADAT. I'm horrible at writing, I'm sure that all the, if anybody's watching this that's a computer scientist is probably cringing at my notation. I am not a coding expert by any means, so please feel free to use, probably better variable notation, but bear with me for the moment. So that's our acceleration data. So to calculate our DFT, we know from our previous video, we have to kind of do this notation. We have to kind of create and do this summation here. So we need to take the y values, which we've already kind of taken the acceleration data at different points or different points in time, and then do this summation for each harmonic coefficient. So we're going to calculate the first harmonic, then we're going to calculate the rest of the harmonics here. So let's take it step by step. So if I just wanted to calculate the first harmonic, what I would do is something like this, build a table. So if I want to calculate the first harmonic, and actually let's do this. I'm going to try this and make this side by side. I'm going to shrink this a little bit. Again, I apologize for this not being as polished. And I'm going to kind of move this around a little bit. There we go. And I'm sure, again, you all are cringing and you probably know all the secrets to how to automatically resize this, but I am stuck in my ways of not being technologically proficient as you all. So bear with me for just a little longer and we'll get this guy going. All right, so I want to see side by side to kind of show how we could write this equation. So let's say I want to calculate the first harmonic. So A1. So all I would have to do, or you could do A0, but you're going to see A0. Actually, let's do it for A0. Doesn't really matter, and we'll see what's going to happen in a second. So I want to create a table. So actually, first I want to go 2 divided by big N. And then I need to create kind of this table or sum. So we're going to multiply this by the sum of that. Now, there is a function sum in Mathematica, but instead we're going to use this function called total. So total is basically going to give us the sum. And I'm going to take table because I want to take out from ADAT each successive point. So table is going to grab me, actually let's break apart how a table works in a second. So I need to take out each value y of r and multiply it by this cosine here. And I need to change values of r here and here. So what I'm going to do is do a table where I take out ADAT. So I'm going to grab, because if I want, so if I want the first data point of ADAT, that's what it gives me. If I want the 10th, it gives me this. So I'm going to do a table like a for loop and grab each of those successive values. I'm going to multiply that times cosine of 2 times pi times I. I is basically our r, that's the nice thing about Mathematica. Let's keep it consistent. Let's do r so that it matches with this expression. Times, what is the value of my n? Here it's just going to be 1. Divided by big N. That's it. Now I'm going to iterate that from r goes from 1 to length of my ADAT. Length is just saying like how long, how many r's do we have essentially. So the length of my ADAT, the number of my big N, it's big N too. So we could actually rewrite it. I like to use that length because that's a more general way to work with your list, but let's just keep it big N. How about that? And that's what it gives me. It's just pulling out those values and multiplying. So you can see the values change slightly depending on kind of the values here. So this gives me basically just that sum. But again, we need to sum this, right? So total will give me the sum of that value. So total is that. But remember, we have to multiply by 2 divided by big N. And that's my first harmonic coefficient for n equals 1. Now, do I want to do this each time and just change essentially this variable little n here? No, I want to write another table. So I want to do another for loop process. So I don't have to do much work at all. I can just kind of run this code and let it go. So now I want to iterate for little n. So I want to go from n, and I'm just going to go right now from 0 to big N. Now we know that, and because I want to show this, and I kind of talked about this in the last video, or in the kind of previous video when we were talking about DFT and spectral aliasing, we know that we can only sample basically to n over 2 times delta f, right? Our Nyquist frequency. But I want to show you why you get this kind of mirror symmetry and show you that example here. So let's do this. And let's plot this, because you can see the mirror symmetry. So let's do list line plot. Look at these harmonic coefficients. You see the mirror symmetry here? It's really, I really like this example to kind of show that right at that Nyquist frequency, all you're seeing is just a symmetric plot range. So beyond the Nyquist frequency, you're not measuring any new frequencies. It's just this mirror image of itself across this line. So it's really nice. And you can see here, look at first value, last value, second value, second last value. So once you get beyond big, n over 2, they just mirror each other. So I'm going to go from 0 to big N by 2. Because that is what we should be properly doing in order to kind of sample again correctly in these frequencies. So I hope that makes sense. We went through it fairly quickly. But these are your A sub n's. And now the nice part, if I want to do B sub n, all I'm going to do is change this variable. And then all we do from sine to cosine, that's it. So I got my A sub n, I got my B sub n. Now I need to calculate what is my C sub n. And we need to calculate, we need to basically plot our frequency spectrum here. So I'm just going to kind of create a list. So C sub n equals, it's going to be a table of A sub n. So I'm going to do, again, this is just the table notation. I'm going to square this. I need to do the square root. I already messed up. That's why so A sub n I squared. And I'm just going to do an iterative list squared and I from again 1 to the length of my list A sub n. Those are my C sub n's. So now I need to also create what are my x-axis values. So my delta f's, right? So this is why we needed to calculate the delta f initially. So my x-axis values, so my frequencies, I'm going to do a table from I equals I times delta f, because again, we can only do integer values of delta f, right? So I from delta f from I equals 0 to the length of Cn, That's it. There it is. So we start at this null frequency because, again, we started from 0 here. And then our first fundamental frequency, delta F, is this. And we multiply by n divided by 2, n over 2. And then this is your maximum frequency here. So with that, we can now plot. Let's do, and I have a kind of a nice, I'm going to kind of cheat here for a second. I have this nice, you've seen this in the mathematical notebook. I'm going to transpose. I want on the x-axis, my frequency. This is frequency spectrum times Cn there. And that did not, that did not go well. So that's why you always kind of check your code here. So we are going to go from check the length. Whenever you have this transpose error, you're going to do Cn and length. Obviously intended this to show you this error. So we want to go, we're too large here, so we need to do subtract 1. So now we're good to go. Because again, we're starting at 0 here, so we had to subtract that value. So yes, this is your frequency spectrum. I'm going to blow this up now for this particular length. So we know, or we anticipate, this is our dominant frequency, our resonant frequency is about 12.5. Exactly 12.5. So you can, what I did there real quickly, I right-clicked in here, get coordinates, and then I can just find this point. So we need to make sure, so that is our experimental frequency. So we found that value. So you're going to calculate precision error with this, and you are going to, do the 5 intervals, see which, calculate the Fourier spectrum for each of those 5 points, and you're going to kind of see what is my precision error. Now, bias error for for this experimental data. The bias error can really only come in if there's uncertainty in time here. So the bias error here is going to be essentially negligible. So there's no bias error for the experimental frequency. There's no precision error for the theoretical frequency. Now, coming back to the theoretical frequency, this data point was for what? 0.36 meters. So let's look at our F. So our F is, I'm going to substitute it in because I know these values. So let me, give me one quick second. Excuse my late values here. I know that the nominal values for H is going to be 3 millimeters. So 3 times 10 to the minus 3. Again, you know in this class, we always use HI. The length was 0.36. The length goes 2. I'm just replacing it. So I'm not assigning variables because I want to change these values later. The length goes to 0.36 meters. I want my Y is the Young's modulus, so it's 16.9 gigapascals times 10 to the 9th. This giga is 9. I know my rho is going to be 2.71 times 1,000 kilograms per meter cubed, because again, we need to be in SI units. And I think that should about do it. So that should be this is my theoretical frequency for that specific beam length. So you'll notice there's a difference there, right? We're getting about 12.5, and then the theoretical value is 18. But again, that could be the differences that we've talked about in the beginning of this video. Plus, we haven't calculated the total uncertainties yet. So those error bars might still overlap here. So don't kind of freak out just yet. And again, there's some difference in this, this theory is you took into account the cantilever beam assumptions. So it might not match with our experimental details. Like that's not, the experiment, you get what you get, you analyze, and you kind of determine what were the largest uncertainties and how do we kind of decrease those? What are the differences between, kind of experimental results and otherwise? But one important thing you have to check about. So right here, this is, so at about 18.6, we should be getting our theoretical frequency. So there's an issue, right? What is our delta F? It's in intervals of 0.5. So to hit that 0.6 value, we might have spectral leakage here. So you might want to kind of talk about that in the lab. That could introduce some additional uncertainty or differences. So you're not sure which, is the real dominant frequency. The other thing we want to make sure, what was our sampling frequency here? So let's go save that variable. So our FS is 50. What was our rule to avoid signal aliasing? We need to make sure that our experimental or our sampling frequency, FS, is at least twice as large as the frequency that we're trying to measure. So 18.6 times 2, we are at least greater than that. So be sure to double check for all of the lengths that you're given that you're not aliasing your signal. So you need to make sure FS is at least twice that value. So think about that. So you want to analyze these do the same procedure for all the different iterations, all those different experiments for each length. And then you want to kind of make a plot of the experimental frequency and the theoretical frequency versus length and show those total uncertainty error bars. So yeah, that's about it in a nutshell. So if you have any issues with this, if you have any more questions, if you need my help debugging the code, please let me know. And I hope this was helpful. And yeah, I will see you all in a couple hours in lab. So have a great day. And yeah, if anything comes up, be sure to let me know. Thanks.